So now f double prime. Negative stays outside. The denominator gets squared. And now, the quotient rule. Top prime, 4x minus 8 times the denominator minus the top. Watch me run out of room. I always do. Almost always. Times the denominator prime, 2 times x minus 2, yay, times the inner function prime, which is 1. I don't have to write it. Please don't start distributing. Look and observe and note that there is a common factor. Pull that out. Always try to take a moment and look and say, can I factor out something? Yes, we can. We can factor out at least x minus 2. So the negative stays outside. X minus 2 over x minus 2 to the 4th. Eventually, I'm going to do this. Okay, so this is gone, but there is still one left in there. 4x times x, 4x squared. 4x times negative 2, negative 8x. Negative 8 times x. Negative 8 times negative 2. This is gone. So now negative 2 times this. Negative 2 times this. And negative 2 times this. I managed to fit it in. Wow. A miracle happened. And look, they must have worked their steps backwards. There is no other way. Positive 16x, negative 16x. Positive 4x squared, negative 16x, 14. Negative 4x squared with positive 4x squared. So this is a negative 6 with a negative in front. Positive 6 at the top, nothing else. Wow. They must have worked their way backwards. Nice. Thank you. Okay, then. So then the second derivative is negative. Again, everything is gone with minus minus. So it's positive 6 over x minus 2 cubed. So this, again, is never 0. How come? Because the numerator should be 0 for a fraction to be 0, but 6 can never be 0. And now, careful, because the power 3, you cannot conclude that the sign is always, so never 0, so no inflection point, or point. So please remember, this gets split into x minus 2 squared and x minus 2. This is always positive. Everything is always positive, except this. This could be positive, could be negative. The reason why I split it like this is because I don't need to worry about x minus 2 squared. Who cares? It's positive. I need to worry about one of these. This alone gives the sign of f double prime, of x, of course. Okay, then, so can anyone tell us where is this positive and where is this negative? And I'll put it in. I didn't hear, but I'm assuming you said negative here.
Yeah, and it's positive.
Very good. I put the sign immediately. No inflection points. Concave down, concave up. That's it. I don't need, and I will not waste my time looking at any of this. This is gibberish now. Doesn't mean anything anymore. All I need is this. Nothing else. Nothing else matters. No other calculations mean anything to me. And they shouldn't mean anything to you. You know what I mean. I'm making a point, of course. First, I have to start with the asymptotes. I always start with the asymptotes. I have to graph the function y equals negative 2x plus 1. When x is 0, y is 1. So 0, 1. When y is 0, negative 1 equals negative 2x, which means x equals 1/2. 1/2, 0. I need 2 points for a line. I have the y-intercept and I have the x-intercept. And I know it has to look like this. It's a negative leading coefficient, negative slope. It has to look like this. So 0, 1, and 1/2, 0. I graph the slant asymptote y equals negative 2x plus 1. Please label everything, always, so you know what you have. So, of course, the slant asymptote and the vertical asymptote are not part of the graph. They cannot be solid lines. So please remember that. Good. Okay, so now I read my table. After I plot the ordered pairs I have. I don't have much, but I have a negative 0.20. I have 0, negative 1/2. And I have 2.7, 0. The function comes from approaching the asymptote towards from infinity, crosses the x-axis, crosses the y-axis, and goes to negative infinity on the left-hand side of the vertical asymptote. From positive infinity, crosses the x-axis, crosses the y-axis, and goes to negative infinity on the left-hand side of x equals 2. So this should be closer, so I'm having a little bit of difficulties with these. This is not a straight line, but how can I plot the negative 0.2? I can't. So it should be a little bit closer here. Okay, so don't think that this is a straight line. It's not a straight line. Good. We're finished with this. It has to approach asymptotically, we say, has to approach the slant asymptote, has to approach asymptotically the vertical asymptote. On the other side, coming from positive infinity on the right-hand side of the vertical asymptote, crossing the x-axis at 2.7, 0, and going to negative infinity. Approaching the slant asymptote. So from positive infinity, crossing, of course, my units are not perfect, sorry about that. So, and then approaches the slant asymptote, approaches the vertical asymptote, approaches the slant asymptote, approaches the vertical asymptote. This is it. So what is different from everything else we looked at, right? Opening down, opening up. What is different is the slant asymptote. Nothing else is different here. Is this okay?
Is this okay? Okay. So, of course, if you want to graph this, that's fine. Just to check, you can. And you go to y equals. Do not forget to put in the slant asymptote. The calculator doesn't know anything about it. And the function, it's a rational function. It has to have parentheses. Who knows where my function is? I see it now. Plus 5x and minus 2x squared. Close the parenthesis. Now divide by x minus 2.
Okay, and now we'll let's look at the graph. Yeah, the standard viewing window should work. Here it is. Here it is. Here it is. Yes, the slant asymptote. It does not show the vertical asymptote, but you know to put it in. Perfect. Thank you. Thank you for your contribution. Thank you for saying yes. Thank you. Okay. Now, I would like to go back to something we skipped. So I think I'm on page 5. Yes. So we skipped 2 theorems in 4.2. One is called Rolle's theorem. So we are done with graphing. That is done. Now we are looking at these 2 theorems, and then we're going to look at Newton's method. We should, for these 2, we probably need half an hour together. So then we can start the last section, which requires more time. Rolle's theorem. So this mathematician said this. Number 1, if a function is continuous on the interval a comma b. Number 2, if it is differentiable, at least on the open, it doesn't have to be at the endpoints. We don't care about the endpoints. But it has to be differentiable at least between a and b. And number 3, if f of a equals f of b, then I'll leave some room. You will tell me what to write. Let's look at the graph. So here's the interval a comma b. So here's the function that is continuous and differentiable. So I'll say f of a equals f of b here. So the function starts at this point and ends at this point, because that's what it says. F of a equals f of b. This is the closed interval, and it's differentiable on the open interval because we don't care whether it's differentiable at this point and this point. So what can the function do? It's continuous and differentiable. So it can do this. That's one option. It can do this. I'm not going to write it though. I can write it, I can graph it on a separate. It can do this. As many times as you want, right? 1, 2, 3, 4, whatever. Or it does once, or it does once, or it does this. Right? So continuous and differentiable, starting at this point and ending at the same point. Then there exists a point C such that f prime of C is at least 1.
Theorem?
Of course. So it must have a term. By term we mean max min. At least 1. It can do it so many times. It can have C1. Let me graph that for you. It can do this. So it has a C1. It has a C2. It has a C3. So it can have any number, but at least 1. In other words, for a continuous and differentiable function to start at one point and end at the same point, it has to have a term, at least 1. What does the term mean? It means a max min. What does a max min mean? The derivative is 0. That's Rolle's theorem. So let's look at an example. Very simple. So let me open here. It's much easier if I do it with you. Okay, so we want to go back to 4.2. Just a simple, is it 4.2? Yes. Okay. Just a simple application. So please choose very simple application. Verify that the function satisfies the three hypotheses of Rolle's theorem on the given interval. Then find all numbers C that satisfy the conclusion.
So in number one, we will say that f of x is definitely continuous on this interval.
It's always continuous, including this interval, of course. This is a continuous function. Number two, f of x is differentiable on this interval. It's differentiable everywhere. This is a smooth continuous function. It's always differentiable. Number three, I don't know. Number three, I have to show that f of pi over 2 and f of 3 pi over 2 will be the same. If they are not the same, then Rolle's theorem is not applicable. If they are the same, then I will draw the conclusion and find C, at least one. Okay, so I have to plug it in. So pi over 2 divided by 2 is pi over 4. So sine pi over 4 is the square root of 2 over 2. 3 pi over 2, sine of 3 pi over 4. 1, 2, 3. 3 pi over 4 is here, and the answer is the same, because sine is positive in the first and the second quadrants. So all three conditions are fulfilled. Hypothesis of Rolle's theorem. And then I'll say then, by Rolle's...
We can't see your paper.
Uh-oh. Sorry. I forgot to stop sharing. Sorry. Okay, let me start from the beginning. So we had this function. The interval was given to us. Sorry about that. So sine function is continuous everywhere. So I wrote f of x is continuous on this interval. Of course, I should write here parentheses. Of course, it's at least on the open interval. Same thing. F of x is differentiable because it's a continuous function and it has no cusps, corners, and so on and so vertical tangents, right? So this is always differentiable, always continuous. Then I have to show that f of pi over 2 and f of 3 pi over 2 are the same. If they're not the same, then Rolle's theorem is not applicable. But when I plug in pi over 2 here, pi over 4, sine pi over 4 is the square root of 2 over 2. Now when I plug in 3 pi over 2, that becomes 3 pi over 4. And 3 pi over 4 is here. So pi over 4 is here, right here in the middle of the first quadrant. And 3 pi over 4 is right here in the middle of the second quadrant. So both have the same height. If they both have the same height, they have the same sign. So then all three conditions or hypotheses of Rolle's theorem are fulfilled. Then by Rolle's theorem,
I will find there exists at least a C
in the open interval pi over 2, 3 pi over 2, such that f prime of C is 0. Okay, so I have to find f prime of x, which is cosine x over 2 times the inner function prime. And I have to set this equal to 0. So I'm looking at between pi over 2 and 3 pi over 2. So this is pi over 2, and this is 3 pi over 2. We're talking about this part of the unit circle. So where is cosine x over 2, 0? Okay, so where is cosine x over 2, 0? When the angle, in other words, when x over 2 is and when x over 2 is. What angle has cosine 0?